let's now jump into the washer method. It's really just kind of a slight modification of the disk method. Now, the idea here is rather than a solid, we have something or a solid that has a hole in it. If you have a solid with a hole, then we kind of refer to that as being a washer. So think of it like something like this. Now keep in mind that my artistic skills leave much to be desired. So see, if you look in this direction, what you see is a disc with a hole in it that's kind of moved along some axes. So just for notation here, I'm going to refer to this distance right here as W, and this distance here from the center of this washer to the outer edge as capital R, and this distance from the center to the inner edge of the hole, small r. So the volume of the washer, first of all, if this was a solid and I just moved it along, it would be pi r squared W. Right? Let me write that down. Pi r squared W. So that would give me the volume of this, well, it would be like a pipe looking thing, a solid pipe. But if I punch a hole in it, what I need to essentially do is take this volume and subtract from it this inner volume. So the way I do that is simply by pi times r squared, that's going to give me the outer volume, minus little r squared, that's the inner. So now I've got this piece left over. I'm simply dealing with this piece right here now. That minus w. So again, capital R is this outer radius, small case r is the inner radius, and w is the width of this washer. So one function is going to define the outer radius. I use capital R, so I'm going to call it r of x, cap r of x. And another is going to define the inner radius, and I'm going to call that little r of x. So what I'm going to end up with is the volume will be equal to pi times the integral from a to b. This a to b represents the this width w, times r of x squared, that's the outer radius, dx, minus pi times the integral from a to b of little r of x squared, that's the inner radius, dx. Now, the way I drew this, these r's are constant. But what if they're not constant? What if I have some other shape on the outside? Maybe rather than being straight like this comes up and down and so forth. Maybe this inner radius does other things too. That's why we need to represent the radius with a function rather than simply a constant number. As I drew this, if I have the x and y axes set up, these are both constants, so these would simply be numbers. But I need to consider the fact that they may not be a constant. This will obviously simplify to pi times the integral from a to b of r of x squared minus little r of x squared dx. And this is the basic formula that we use when we're trying to find volumes of solids using what's known as the washer method. So let's go ahead and take a look at an example here. So I want to find the volume of a solid formed by revolving the region bounded by f of x equals x and g of x equals x squared about the x-axis. So let's go ahead and draw a picture of this. Whenever possible, always draw pictures to help you see what's going on. See, f of x equals x and x squared. So f of x equals x looks like this. X squared looks like this. I should have brought this out a little bit farther because I happen to hit it where it intersects. And I'm going to take the region that's bounded by it. Well, that's this region right here. And that is what I'm going to revolve about the x-axis. So when I do that, what I'm going to end up with is, let's see, right about here-ish. So my solid is going to be like this. And if I look into it, this piece right here, that's white, right in here, that's going to be a hole. So it's going to be like a cone with a piece of it dug out is really kind of what it amounts to there. So one of the first things I need to figure out is what are the coordinates of this point and this point. I need to know how far I'm going to be integrating. So just set the two functions equal to each other. X squared equals x. That implies that x must be equal to 0 or 1. So this is 0 and this is 1. So I know I'll be integrating from 0 to 1. Now what I need to do is figure out what my radiuses are. So notice on 0 to 1, the open interval, that x squared is less than x. So that tells me then that r of x, the outer radius, will be x, and little r of x, the inner radius, will be x squared. So that then suggests that the volume is going to be pi times the integral from 0 to 1 of the outer radius x, quantity squared, so that'll be, I'll write it like this so you see them squaring this outer radius, minus the inner radius squared, which is x squared squared, dx, which is obviously pi times the integral from 0 to 1 of just x squared minus x to the 4th dx. So that's going to be pi times x cubed over 3 minus x to the 5th over 5 from 0 to 1. And that will give me pi times 1/3 minus 1/5, which gives me pi times 5 minus 3 over 15, which is 2 pi over 15. So the volume is going to be 2 pi over 15 cubic somethings.